Let's look at some examples of lemniscates. So the lemniscate function as a polar function in general is going to have the equation r squared is equal to a squared sine of 2 theta, or it could be r squared is equal to a squared cosine of 2 theta. And it's always going to be 2 theta. You can change the 2 to different values, but we're just going to always keep it at 2 theta. So in this example I have here, we're looking at the graph of r squared is equal to 5 squared sine of 2 theta. And you might see it, instead of 5 squared, you might see it written as 25 sometimes. But so r squared equals 5 squared sine of 2 theta. And the graph that we get for this looks like two loops going in opposite directions. They both meet at the origin, and they have a radius of 5. Each of them extends outwards to the circle of radius 5. So again, in the polar coordinate system, we have these concentric circles. Each circle is a distance of 1 unit further out from the origin. So the two petals have a radius of 5, which we get that 5 from our equation, right? The a squared is 5 squared. And for sine, we see that the graph looks to be slanted, sort of like there's an axis of symmetry running diagonally along the y equals x line, or along like the 45-degree angle line. So r squared is equal to 5 squared sine of 2 theta is two loops, axis of symmetry along the 45-degree line, and each petal has a radius of 5. So that's kind of just a quick summary of what we see for this equation. What happens if we change the a value? Right now, with an a value of 5, again, we see the petals, the two loops extending outwards to a circle, the circle of radius 5. So what happens if we change those a values? So instead of a 5, let's say we have a 7. So if we have r squared is equal to 7 squared, which you might see that as r squared equals 49 sine of 2 theta, we still have the same two loops. They're still oriented and symmetric along the 45-degree line, the y equals x line. But this time, they both have a radius of 7. They extend outwards to the circle of radius 7. So that looks like that's going to hold true regardless of what we change the radius to. So if we did r squared equals 10 squared sine of 2 theta. So if the a value is 10, still the graph is oriented on that diagonal line, and the petals, the loops each have a radius of 10. So what happens if we switch this to cosine? So if I have the graph of r squared is equal to 10 squared cosine of 2 theta, I still have two loops. They both meet at the origin, and they both have a radius of 10. They extend outwards to the circle of radius 10. The only difference is that instead of the graph being slanted diagonally, so it's oriented on that 45-degree line, they are now oriented on the positive and negative x-axis. So it just changes whether we have sine or cosine. It just changes whether we have where our axis of symmetry is going to be. Is the axis of symmetry the y equals x line, or is it the x-axis? Just to have a quick summary of this, again, the lemniscates, the equations have the form r squared is equal to a squared sine of 2 theta, or r squared equals a squared cosine of 2 theta. If it's a sine graph, then it's symmetric with the y equals x line. If it's a cosine graph, it's symmetric with the x-axis. And regardless, each of the graphs will always have two loops, and the radius of each loop is the value of a. So let's look at a few examples here where we are given the graph and we want to write the corresponding equation. So in this first graph, we have two loops. They each have a radius of 4, so they extend out to the circle of radius 4. And they're oriented, both loops are oriented on the x-axis. So because they extend out to the circle of radius 4, I know that the a value has to be 4. And because they both are oriented on the x-axis, I know we're looking at a cosine graph. So again, the equation will be r squared is equal to 4 squared cosine of 2 theta. And it's always r squared, it's always a squared, and it's always 2 theta. So I could just simplify this really quick. R squared is equal to 16 cosine of 2 theta. All right, let's try another one. This time we have two loops again, but this time they are oriented along the y equals x line, that 45-degree angle mark, which means we're going to have sine, and then the radius of each of these petals extends outwards to the circle of radius 8. Okay, and so that means the a value is going to be 8. So we're going to have r squared is equal to 8 squared sine of 2 theta, or we could rewrite that as r squared is equal to 64 sine of 2 theta. All right, let's try a couple of graphs where we're given the equation and we want to sketch the graph. So for this first one, we have r squared is equal to 9 sine of 2 theta. So that 9 we could think of as 3 squared, which means the a value is 3. And because it's a sine equation, I know it's going to be oriented along the y equals x line. So that 45-degree angle, pi over 4. All right. And it's going to extend outwards to the circle of radius 3. So if I were to just kind of draw a dotted circle, just to kind of help me draw the graph here, I'm going to draw a dotted circle of radius 3. And then I'm going to draw two loops, starting at the origin and looping out to that dotted circle. And we're going to just kind of draw them diagonally along the 45 line, or the y equals x line. So we're going to get two loops on the y equals x line, angled at 45 degrees, and they each have a radius of 3. All right, let's do one more. R squared equals 25 cosine of 2 theta. So the 25 tells me the a value has to be 5, and because it's cosine, I know it's going to be on the x-axis. So again, I'm just going to do the same thing here. I know I have to have this circle of radius 5, and I'm going to draw two loops at the origin. So from the origin out 5 units along the x-axis, and then to the left from the origin out to the circle of radius 5, and then back to the origin. So those are the two loops. So that's the graph of r squared equals 25 cosine of 2 theta.